Welcome to Space Dreams documentary. Tonight's journey follows the life cycle of massive stars, from their quiet birth inside cold clouds to fierce nuclear-burning powerful winds and the final fate that reshapes their surroundings. Expect calm narration, vivid cosmic imagery and deep science made soothing and clear. If this kind of space documentary helps the mind unwind, please like the video and subscribe to Space Dreams documentary. It truly supports the channel, and it keeps these long, restful stories coming. Now let the universe slow down. In the cold dark of a molecular cloud, a massive star begins as a quiet imbalance. The future scale is decided early when gravity gathers gas faster than escaping light can slow the collapse. At this distance, the cloud looks smooth at first. Then faint filaments appear. They curve like smoke strands that never fully mix. Dust thickens along the filaments. The darkness deepens by degrees. In one bend of a filament, density rises. It rises almost imperceptibly. A pocket becomes heavier than its surroundings. The first change is not brightness. The first change is motion. Gas drifts inward from many directions. The flow is uneven. It follows the easiest paths. A soft boundary forms where inflow meets resistance. It is not a wall. It is a gradient in pressure and temperature. That gradient marks the beginning of a center. In that center, time starts to feel different. The collapse is still slow on a human scale, yet it is swift on a stellar one. In a few 100,000 years, the core can change from diffuse fog to a compact seed. That span is like a single breath compared to the long burn of a star. The cloud does not fall as a perfect sphere. A slight twist is always present. It may come from nearby turbulence. It may come from an older ripple in the gas. Even a small twist matters. As the core contracts, rotation speeds up. The inward flow flattens. A disk takes shape around the densest point. The disk is thin compared to its width. It carries most of the angular momentum. A narrow, dark lane can cut across it. That lane is dust seen in silhouette. It is a physical shadow. It appears because the disk blocks and scatters light. The shadow is an early clue that structure is forming, not just density. In that region, gravity does two jobs at once. It compresses the center. It also organizes the outskirts into streams. The streams look like faint arms. They feed the disk. The disk feeds the center. This is the first unlock. A massive star is not built in a single rush. It is built through a regulated funnel. Material joins the disk. It loses energy through radiation. It drifts inward in steps. The center grows without needing a smooth fall from all sides. The key concept is accretion. Accretion means growth by steadily collecting surrounding material. The disk makes accretion efficient. It turns chaotic inflow into ordered supply. It also sets the early conditions for mass. In a massive core, the supply is heavy. The disk can be thick with gas. Its inner edge is hotter. Its outer edge is colder and dustier. Between them, temperature falls with distance. That slope is another physical detail. It shapes what can condense and what stays vapor. Light behaves differently across that slope. Shorter wavelengths scatter off small grains. Longer wavelengths slip between grains. Visible light struggles to escape. It is absorbed and re-emitted. The center stays hidden behind a veil. That is a limit of observation. The inner few regions cannot be seen directly in ordinary light. Only indirect signals can escape. Heat can leave as infrared glow. Motions can be traced through radio emission. Yet even those signals blur together. The disk is small at cosmic distances. The details smear into a single bright knot. The shape must be inferred from patterns in light and motion. A model can fit more than one structure. That uncertainty is part of the early story. Still, the physics remain steady. As mass piles onto the central seed, pressure rises. The temperature rises with it. Compression heats the gas. The heat does not make the collapse stop at once. It makes the center brighter in wavelengths that can get out. The glow is gentle. It is not yet a star's surface. It is a warm cocoon inside dust. The second unlock arrives here. Heat does not need fusion to matter. Before any nuclear burning gravity already turns motion into warmth. The center becomes a protostar. A protostar is a forming star powered mainly by gravitational heating. Like driftwood gathering at a river bend, the growth is shaped by flow. Not every piece arrives at the same time. Some pieces circle first, some pieces are swept away. The gathering still continues. Around the disk, outflows begin. They are not a choice. They are a consequence of rotation and magnetic fields. Field lines can thread the disk. They can guide some gas upward and outward. Twin cavities can open above and below the disk. The cavities are clearer than the surrounding cloud. Their edges are sharp in places. Dust outlines them as bright rims. The scene becomes a slow hourglass carved into darkness. That hourglass is a visual anchor. It shows how a forming massive star reshapes its environment early. The outflow reduces pressure near the poles. It also clears channels. Through those channels, more radiation can leave. This changes the balance. In massive formation, radiation pressure matters. Radiation pressure is the push of light on matter. The definition is short. The example is simple. Dust grains absorb photons. Each absorbed photon carries momentum. The grain receives a tiny push. Many photons make a steady push. The reason it matters is direct. In a very luminous protostar, the push can oppose infall. It can slow the feed. This does not end growth by itself. It redirects growth. Gas can still flow along the disk plane where gravity wins. The disk acts like a shield. It absorbs and reroutes radiation. It also funnels material inward. A quiet contest forms. Gravity pulls. Light pushes. The contest is not symmetric. It depends on where the gas sits. It depends on how dusty it is. It depends on how clumpy the inflow becomes. Clumps can fall in despite the light. They are denser. They have more inertia. This is another small payoff. A massive star can keep growing even while becoming bright. Growth continues through geometry and uneven flow, not through a single perfect collapse. The scale shift becomes clearer here. The disk spans distances that can rival the size of a planetary system, though no planets are needed for the image. The core at the center is far smaller. In the center, seconds matter. In the outer envelope, years matter. Across the cloud, the entire process spans hundreds of thousands of years. The story contains many clocks at once. The view pulls back. Filaments still feed the region. The disk still turns. The cavities still widen. The cocoon still glows. In time, the central temperature approaches a threshold. The gas becomes hot enough for hydrogen fusion to start. The exact moment is hidden. It happens behind dust. It's not marked by a sudden flash that must be seen. It is marked by a shift in support. Pressure from fusion begins to assist pressure from heat. The protostar becomes a true star. The surface is not calm yet. The envelope can still be thick. Mass can still be arriving. The star's early life is not a clean beginning. It is a handover from gravity-driven heating to fusion-aided stability. The section ends with a soft turn. The forming star is now a dense core wrapped in a feeding disk. The next step follows the core inward where balance and burning begin to settle. A massive young star glows behind dust, yet the true change is balance taking shape. The star steadies when inward fall, and outward pressure begin to match in the deep interior. At this distance, the surrounding cloud still looks like a dim curtain. Within it, a disk turns like a broad, thin band. The band is darker along its midline. That darkness is a physical shadow. Dust blocks short light and scatters it sideways. Above and below the disk, cavities remain clearer. Their edges shine softly where grains catch and re-radiate heat. The scene holds on the hourglass outline. It widens slowly as outflow continues. The center brightens without a sharp surface being visible. Light behaves as filtered warmth. It emerges in longer wavelengths that slip through dust. The early anchor rests on a simple idea. A forming massive star can be bright and still be growing. Growth continues through the disk. The disk feeds the center in a controlled stream. The stream is not smooth. It arrives in clumps. Each clump carries extra weight that helps it push inward. This resolves a quiet question. How can the star keep gaining mass while light pushes outward? The answer lies in geometry and uneven flow. The disk shields some infell from direct radiation. Clumps bring inertia that is harder to deflect. The first core concept remains accretion. Accretion is growth by collecting surrounding gas steadily. In this stage, accretion becomes a negotiation. Gravity pulls inward. Heat and radiation resist. The negotiation happens at a boundary called the accretion shock. Gas falls onto the dense core. It slows abruptly. The slowdown turns motion into heat. A bright ring can form where the impact is strongest. The ring is not a hard edge. It is a gradient of temperature and density. That gradient matters. It sets how energy leaks outward. It also sets how quickly new gas can settle. A single number can anchor the scale. The disk can span about 100 astronomical units. That is about 100 times the distance from Earth to the Sun. The comparison is only a yardstick. No human scene enters. The scale shift follows naturally. The dense center is far smaller than the disk, yet the disk controls how the center grows. The view drifts from the wide band inward to the hot inner rim. The rim glows more strongly. Dust closer in can sublimate and vanish. Gas becomes more transparent there. The inner region becomes a place where light can begin to escape more directly. This unlocks a second piece. The brightest output does not come only from a star's surface. It can come from gas crashing down and heating at the shock. The star is still assembling itself. Its light is partly the soundless record of falling matter. The second core concept enters gently. Radiation pressure is the push of light on matter. In a massive protostar, that push acts most strongly on dust. Dust grains absorb and re-emit photons. Each interaction transfers a tiny momentum. Many interactions create a steady outward force. The example stays simple. A thin veil is easier to move than a compact clump. The reason it matters is direct. Radiation pressure can carve pathways. It can widen the polar cavities. It can also halt some inflow near the poles. Yet the disk remains a sheltered route. The star grows along the plane where gravity dominates. The scene shifts to the cavity wall. The wall is not smooth. It has ripples and knots. Those knots are denser pockets that resist the outflow. They cast small shadows into the cavity. The shadows drift as the gas moves. A new visual anchor settles here. A slow ribbon of dust curls along the cavity edge. It looks like powdered pigment pulled along a wet brush stroke. The brush stroke is space itself. The dust traces flow lines without needing any instrument. The rhythm stays gentle. Pressure rises in the center. Temperature rises with it. The core approaches a threshold where a new support can appear. Hydrogen fusion is still not fully established, yet the gas becomes ionized. Ionized means atoms lose electrons in hot conditions. The example is plain. Heat shakes electrons loose. The gas becomes a mixture of charged particles. The reason it matters is practical. Charged gas couples to magnetic fields. This coupling helps launch and collimate outflows. It also changes how energy moves. Convection can stir some layers. Radiation can dominate others. Layers form with different transport styles. A boundary develops between them. It is a physical stratification. It is another quiet clue that the interior is organizing. A payoff arrives in the simplest form. The moment of stability is not a switch. It is a gradual handover. Gravitational heating remains important. Accretion shocks remain bright. At the same time, the core starts to generate energy from fusion in its deepest region. That fusion adds pressure. Pressure resists collapse. The inward drift slows. The center becomes less fragile. The outer envelope still feeds the disk. The disk still feeds the star. The star is now luminous enough to reshape the cloud on larger scales. A bubble begins to form around it. The bubble is not empty. It is a low-density cavity filled with hot gas. Its edge is a shell where sweat material piles up. That shell can be thin compared to its radius. It glows faintly from heated dust. The scale shift widens again. The disk is a local machine. The bubble is a regional imprint. The cloud around it is vast. The process still remains hidden in many wavelengths. That is a limit of observation. Dust opacity prevents direct views of the inner few astronomical units. Different models can fit the same brightness. Spectral lines can broaden and overlap. Motions can be inferred but not seen cleanly. Resolution blurs the inner structure into a single unresolved glow. Even so, the broad sequence remains secure. A massive star grows through a disk. It pushes back with radiation. It clears cavities with outflow. It approaches a stable burning phase without a dramatic start. The ending turns softly forward. The next section follows the star as it emerges from its cocoon. The surrounding material thins and a steadier glow begins to dominate. The first clear light of a massive star does not arrive as a sudden reveal, it arrives as thinning. The star emerges because the surrounding dust and gas stop hiding it so completely. At this distance, the natal cloud still hangs like a dim veil. Yet the veil is no longer uniform. Cavities widen, streams thin. The densest knots drift aside or disperse. The disk remains, but its outer edge frays into wisps. The central glow sharpens. A soft boundary appears where the stellar wind begins to dominate the local gas. That boundary is not a hard shell. It is a pressure gradient that steepens with time. Inside it, the gas is hotter and more ionized. Outside it, the gas stays cooler and dusty. The visual anchor settles on a bright arc. It is a curved rim at the edge of a clearing. The rim shines where dust grains heat and re-radiate. The interior looks darker by contrast, as if a shallow bowl has been scooped out of fog. Light behaves as a sculptor here. It does not carve with intent. It carves because photons carry energy and momentum. The early anchor holds a simple fact. Clearing happens when outward feedback grows faster than new material can fall in. The story becomes a set of checkpoints. First, the star's own radiation heats nearby dust. Then the heated dust re-radiates at longer wavelengths. Those longer waves slip outward more easily. The surrounding gas warms. Warm gas expands. Expansion lowers density. Lower density lets still more radiation escape. This loop is gentle but persistent. The first concept is an ionized region. An ionized region is a volume of gas stripped into charged particles. The example stays quiet. Ultraviolet light knocks electrons free. The gas becomes a faintly glowing plasma. The reason it matters is direct. Ionized gas resists compression more strongly. It pushes outward and helps clear a cavity. The edge of this region can be sharp. It's a thin front where ionized gas meets neutral gas. The front can ripple. It can bow outward where density is low. It can stall where density is high. Those ripples are physical texture. They show the environment is uneven. The second concept is stellar wind. Stellar wind is a continuous outflow of gas from a star. In a massive star, it can be fast and dense. The wind piles into the surrounding cloud and forms a bubble. The bubble has an inner hot zone and an outer swept shell. The shell is where compressed material collects. It is thin compared to the bubble's size. It can glow from heated dust and excited gas. A single number anchors the size without strain. The bubble can reach about 10 light-years across. That span is like the distance a slow, drifting cloud would cross in countless lifetimes. The scale shift is calm. Close in, the wind begins at the star's surface. Far out, the bubble becomes a regional structure in the cloud. The unlock arrives in the middle. A massive star does not simply turn on and remain hidden. It actively changes what can still feed it. The disk may still deliver gas, but the pathways narrow. Accretion continues through the densest lanes. At the same time, feedback clears the easiest routes. Growth and clearing overlap rather than replace each other. The star's surface becomes more defined. Its light becomes less filtered by dust. The spectrum shifts towards shorter wavelengths that were once trapped. The surrounding cavity becomes more transparent. This is a small payoff. Brightness does not only increase, visibility increases because the fog thins. The scene moves along the bubble wall. Dust forms a faint ring around the clearing. The ring is not perfectly circular. It is lopsided, shaped by uneven density. Knots on the ring cast small shadows into the cavity. The shadows slide slowly as the shell expands. A secondary visual moment appears. Fine striations run along the shell like grain in wood. They mark instabilities where hot gas presses on cooler layers. The physics stays restrained. Pressure differences drive motion. Temperature differences drive sound waves and turbulence. Magnetic fields can guide some filaments. Yet no single line is visible directly. That brings a limit of observation. The internal pressure and temperature of the hot bubble cannot be mapped in detail from afar. Emission lines blend. Different densities emit differently. Models must assume geometry that cannot be fully confirmed. A signal would carry integrated information. It would smear small structures into an average glow. Even with that limit, the outline remains reliable. Ionization expands. Wind inflates a bubble. The shell sweeps and compresses. The star becomes exposed in stages. Another payoff follows from this exposure. Once the star's radiation escapes more freely, it can halt further collapse in nearby clumps. Only the densest clumps keep falling in. This helps set the star's final mass. It also sets the timing. A massive star's youth is short. It moves quickly from embedded to exposed compared to smaller stars. The transition does not need dramatic events. It needs time for feedback to outpace inflow. The view pulls back again. The bubble sits inside the wider molecular cloud like a clear pocket. Filaments outside it continue to drift. New dense knots can still form farther away. The region becomes a patchwork of dark and faintly glowing zones. In that patchwork, the massive star now stands as a bright source. The disk remains as a thin band close in. Its silhouette is weaker than before because the surrounding dust is thinner. The cavities above and below it widen further. The star's wind continues to stream outward. The boundary of the ionized region continues to move. The motion is slow in a single moment. It is vast over thousands of years. The end of the section turns gently forward. With the cocoon thinning, the star's interior settles into a steadier burn. The next step follows the main sequence phase where fusion becomes the dominant support and the clock of fuel begins to matter. A massive star on the main sequence looks steady, yet its calm hides a strict balance. The star shines stably, because fusion pressure and gravity hold each other in place. At this distance, the surrounding bubble remains a faint cavity. The inner star now dominates the scene. The surface appears as a bright disk with a softened edge. That edge is a limb darkening gradient. Light leaving at a slant crosses more gas. It scatters and absorbs more. The rim therefore looks dimmer than the center. This simple shading is a physical clue. It shows an atmosphere with thickness, not a hard boundary. The star's interior is the next checkpoint. In the core, hydrogen nuclei fuse. Energy flows outward through layers. The outer layers radiate that energy into space. The first concept is hydrostatic equilibrium. Hydrostatic equilibrium is balance between inward gravity and outward pressure. The example is quiet. If gravity tightens, pressure rises as the gas compresses. If pressure pushes outward, gravity pulls the gas back. The reason it matters is direct. This balance sets the star's size and density for most of its life. The second concept is core fusion. Core fusion means light nuclei combine and release energy. The example stays simple. A small amount of mass becomes heat and radiation. The reason it matters is also simple. That energy provides the pressure that keeps collapse from continuing. A micro payoff lands early. The star does not burn like a flame. It maintains a controlled interior conversion limited by pressure and temperature. The star's brightness can be enormous, but the mechanism is steady. The visual anchor shifts to a slow view of flowing light. A faint halo surrounds the disk. It is not a ring of matter. It is scattering in the outer atmosphere and nearby gas. The halo is uneven. It looks smoother on one side. It looks mottled on another. This texture hints at wind and density variations. The star's wind continues to stream outward. It carries gas away from the surface. The flow is not a single jet here. It is a broad outflow that thickens and thins in patches. Near the surface, small clumps form where the wind cools. These clumps can cast tiny shadows into the outflow. The shadows soften quickly as the gas expands. Another payoff arrives in this detail. Mass loss begins even during the stable phase. The star's future is already being altered. The star is stable in structure, yet it is not closed to its surroundings. The pace of this stage depends on mass. A massive star spends less time on hydrogen than a smaller star. One rounded number can hold the scale. The main sequence lifetime can be about 5 million years. That span is like a single slow blink compared to the age of a galaxy. The scale shift becomes gentle. In the core, reactions happen in fractions of a second. In the envelope, energy takes far longer to leak outward. Over millions of years, the star's composition changes. Hydrogen declines in the core. Helium grows. The core slowly contracts. The outer layers respond by adjusting outward. The surface may change brightness and temperature only modestly at first. The interior change is larger. This resolves a quiet question. How can a star look almost the same while its core evolves? The answer is that the core is a small fraction of the star's radius. Small central changes can be buffered by large outer layers. The star becomes a layered machine of gradients. Density falls outward. Temperature falls outward. Pressure falls outward. Each gradient is smooth, not stepped. The smoothness matters. It is the reason the star can remain stable without violent oscillations. The view drifts inward in imagination. The core is dense and hot. Outside it lies a radiative zone where energy moves as photons. Farther out, a convective zone may exist where hot gas rises and cool gas sinks. Convection here is not a surface boil. It is a slow overturn in deep layers. It forms cells and plumes. Those plumes carry heat upward. They can create subtle brightness patterns at the surface. The patterns are small compared to the star's overall glare. The third concept enters lightly as a supporting idea. Opacity is resistance to light passing through matter. The definition is short. In dense gas, photons scatter many times. In thinner gas, photons travel farther between interactions. The example is plain. Fog blocks a beam more than clear air. The reason it matters is essential. Opacity controls how energy escapes. It therefore controls the star's temperature, structure and size. This also creates a limit of intuition. The interior cannot be seen directly. Only surface light and wind signatures can be measured from afar. Those signatures must be interpreted through models. Different internal layer structures can produce similar surface temperatures. A signal would carry only the integrated effect. It would not map each layer's thickness cleanly. Uncertainty remains in the details of mixing and rotation. Yet the broad behavior holds. Massive stars burn hot and fast. They lose mass through wind. Their cores evolve even while their surfaces appear steady. The visual anchor returns to the limb. The gradient at the edge looks calm. It is a gentle dimming into space. The halo fades into the cavity. The wind continues as a thin haze moving outward. The bubble wall remains far away as a faint arc. The scene holds long enough for quiet rhythm. The star's main sequence phase is a plateau. It is also a countdown in fuel. As hydrogen declines, the core contracts further. Temperature rises. The next section follows this shift. The star's stability begins to tilt toward a new burning stage, and the outer layers start to respond in larger ways. The steady brightness of a massive star begins to drift long before the surface looks dramatic. The change starts when the core runs low on hydrogen and must adjust to keep pressure support. The scene opens close to the stellar limb. The rim still shows a gentle dimming gradient. The center remains brighter than the edge. The atmosphere still scatters and absorbs, yet subtle patterns appear in the glow. They are slow, broad variations rather than sharp spots. Beneath that calm surface, the core contracts. Contraction raises temperature. The core becomes denser. Fusion in the center weakens as hydrogen declines. Gravity responds by tightening its grip. This is the first quiet unlock. A star can brighten and expand even while its core shrinks. The reason is balance. When the core contracts, it heats the layers above it. Those layers respond by expanding. Expansion cools the surface slightly. It also changes the star's size. The second concept enters as a checkpoint. Helium ash is the helium left behind after hydrogen fusion. The definition is short. The example is plain. Like fine powder settling after a burn, helium collects in the center. The reason it matters is direct. Helium does not fuse under the same conditions as hydrogen. It changes the core's ability to generate energy. A new layer forms. Hydrogen burning moves outward into a shell around the helium-rich core. This is shell burning. Shell burning means fusion happens in a layer outside the core. The shell is thin compared to the star's radius, yet it can produce large energy output. The visual anchor settles on a luminous belt under the surface. It is imagined as a broad ring of higher temperature within the envelope. The ring is not visible as a stripe on the surface. It is a structural layer inside. Its physical signature appears as a steeper temperature gradient outward. The envelope becomes more inflated. The star's outer gas becomes less tightly bound. Wind can strengthen. The outflow thickens into a faint haze around the star. The boundary between wind and space becomes more extended. A soft halo grows. It is shaped by density dropping with distance. The halo is not symmetric. It can be slightly flattened by rotation. A faint equatorial density enhancement appears. It casts a subtle shadow into the polar directions. This shadow is a physical effect of thicker gas in one plane. It changes how light escapes. Light behaves as a traveller through fog. In thinner directions it passes. In thicker directions it diffuses and reddens. Another small payoff arrives here. The star's appearance is not only set by internal fusion, it is also set by how its own outflow rearranges the path of photons. One rounded number anchors the timescale. The shell burning stage can last about a few 100,000 years. That span is like a short pause compared to the millions of years before it. The scale shift becomes gentle. Deep inside, pressure changes on timescales of days and months as the core readjusts. Far outside, the envelope responds over years and decades. Across the full star composition shifts over hundreds of thousands of years. The star begins to move away from a strict main sequence identity. It becomes larger. Its surface temperature can drift downward. Its luminosity can rise. These trends happen without needing a sudden event. The interior structure becomes more layered. The helium core is compact and hot. The hydrogen burning shell sits outside it. The envelope above becomes more expanded and less dense. Between shell and surface, energy transport can change. Convection can deepen. Radiative zones can shrink. Plumes can carry heat upward more efficiently. This affects mixing. Mixing gently stirs material between layers. That stirring can bring fresh hydrogen into the shell. It can also bring fusion products outward. The process is slow. It is not a violent churn. It resembles syrup folding into itself in a warm bowl. The analogy remains single and distinct. It explains mixing without needing a list. The physical detail anchors it. Layers blur at their boundaries. Gradients smooth rather than step. That smoothing changes how long the shell can burn. It also changes what the star becomes next. A limit of observation appears softly. The interior boundary between helium core and hydrogen shell cannot be directly imaged. The surface light and wind lines must be used to infer it. Different combinations of mixing and rotation can mimic each other at the surface. A signal would blend contributions from many depths into one spectrum. Resolution cannot separate the layers. Models must assume how efficiently mixing operates. That assumption carries uncertainty. Yet the general direction remains secure. Hydrogen in the center declines. Helium accumulates. Burning shifts outward into a shell. The star swells. The wind strengthens. And the view drifts outward to the wind region. The flow becomes more textured. Small density clumps form and disperse. They create faint mottling in the halo. The halo's edge is not a sharp wall. It is a fading gradient. Farther out, the wind meets the old bubble. A thin interaction zone forms. It is a weak shock that compresses gas slightly. Compression can heat dust grains. A faint arc appears at the interface. The arc is a slow-moving ripple in the cavity. Another payoff settles here. Even before the final stages, the star begins to reshape its surroundings a second time. The early bubble was carved during formation. The later wind reinforces and expands it. The star's path now points toward more dramatic structural change, but the transition remains gradual. The core continues to contract and warm. Helium approaches conditions where it can ignite. The envelope continues to expand and cool. The next section follows the star into stronger mass loss and more unstable behavior. The outward appearance grows more changeable while the interior grows more decisive. A massive star can begin shedding its outer layers while its core grows heavier and hotter. The surface becomes unstable because energy flow and gravity no longer share the same simple rhythm. At this distance, the star fills the frame as a swollen disk with a softened edge. The limb-darkening gradient is still present, yet the halo around the star thickens. It is no longer a faint haze. It becomes a structured wind region with clumps and arcs. A slow shell of gas drifts outward. It is not a single explosive event. It is a dense pulse riding on top of a continuous wind. The shell has a sharper front edge. Behind it, density falls in a gradient. That gradient is visible as a change in brightness across the halo. The visual anchor settles on this expanding arc. It moves like a slow wave in a quiet sea. The wave is made of gas and dust. Light scatters off its grains and then fades as the shell thins. This stage unlocks a simple answer. Strong mass loss is not reserved for the final collapse. It can be built by repeated gentle ejections that add up. The first concept is an inflated envelope. An inflated envelope is an expanded outer layer with low density. The example stays plain. Heat from inner burning pushes the outer gas outward. The gas spreads over a larger volume and becomes easier to lift. The reason it matters is direct. A loose envelope allows radiation and wind to remove mass more efficiently. The second concept is pulsation. Pulsation is a slow expansion and contraction of the outer layers. The definition is short. The example is soft. Like a bellows moving without a loud sound, the star's radius swells and then relaxes. The reason it matters is practical. Pulsation can raise the atmosphere and cool it. Cooler gas allows dust to form farther from the surface. Dust then catches light and feels radiation pressure. Radiation pressure can then push the dust outward. Gas couples to the dust and follows. A micro payoff arrives here. Dust is not just a passive tracer. Dust can become a lever that turns light into outward motion. The scene moves closer to the boundary where dust can survive. There is no sharp line. There is a zone where temperature falls enough for grains to condense. In that zone, a thin band of higher opacity appears. Opacity rises because grains scatter and absorb efficiently. This makes a visible change. The halo becomes thicker and more uneven. Dark lanes appear where density is higher. Bright lanes appear where light escapes through thinner gaps. The star's outflow becomes patchy. It is not a uniform breeze. It is a layered flow with knots. Some knots drift outward and spread. Some knots dissolve. The overall motion remains outward. One number anchors the scale of a single pulse. An ejected shell can take about 1 year to move far enough for its arc to widen noticeably. That span is like a season turning in slow motion repeated in a place with no seasons. The scale shift is calm. The outer shell changes over months to years. The core beneath changes over thousands of years. Over the star's late life, many pulses can occur. Each pulse may remove only a small fraction of the envelope. Together they reshape the star's fate. Another payoff follows. Mass loss changes which final remnant becomes possible. Reducing the envelope can expose hotter layers. It can also reduce the weight pressing on the core. The interior burning continues regardless, but the outer appearance shifts. The star's color can drift. The wind density can rise. The surrounding bubble can be refilled with fresh material. Farther out, the earlier cavity wall receives new impacts. Each new shell strikes older wind. It forms thin shocks. The shocks compress gas into narrow sheets. Sheets can fold into filaments. Filaments catch light as faint threads. The view pulls back to show multiple arcs at different radii. They resemble ripples on a pond after repeated drops, yet no drop is seen. This analogy remains distinct from earlier images. It explains the layered shells without repeating a prior metaphor. The arcs are physical history. Each arc marks a past ejection. The spacing between arcs marks time between pulses. Yet even this picture has limits. That is the limit of observation. The true three-dimensional shape of each shell cannot be fully known. A ring may be a shell seen in projection. A bright arc may be the densest edge along a line of sight. Without full depth, information geometry must be inferred. Brightness can also mislead. Dust temperature changes with distance. A cool region may look dim even if dense. A warm region may look bright even if thin. Models must assume dust properties and clumping. Different assumptions can produce similar outward arcs. The details therefore remain uncertain. The broad mechanism remains secure. Pulsation lifts the atmosphere. Dust forms in cooler lifted layers. Light pushes on dust. Wind carries gas outward. The star loses mass in steps. The inner engine continues to evolve. The helium core grows. Shell burning becomes stronger. The envelope becomes more extended and easier to disturb. The scene returns to the expanding arc. Its front edge fades as it spreads. Its back edge blends into older wind. The halo becomes smooth again for a moment. Then another denser band begins to form closer in. It is faint at first. It is a slightly thicker region of scattering. It marks the start of another pulse. The ending turns softly forward. The next section follows how steady wind and radiation pressure deepen the mass loss, carving a larger cavity and thinning the envelope toward a new stellar identity. As mass loss deepens, the star's outer layers become more like a moving atmosphere than a stable skin. The star transitions because strong winds and radiation steadily peel away the envelope and reveal hotter layers beneath. At this distance, the star no longer looks like a simple bright disk with a faint haze. The surrounding space is filled with structured outflow. A broad pale shroud surrounds the star. It is thicker near the equator and thinner near the poles. The shroud has a scalloped edge. Small arcs and notches mark density variations. Those notches create soft shadows inside the wind. The wind itself becomes the main scene. The visual anchor settles on a crescent-shaped shell that appears within the larger shroud. It is not the same as earlier arcs. This crescent is closer in and sharper. It looks like a thin layer of frost on a curved surface, yet it is gas and dust. The brightness changes across it. The front edge is brighter. The back edge fades into a gradient. This gradient is a physical detail. It marks how density falls behind a compressed front. The first concept is optical depth. Optical depth is how opaque a layer is to light. The example is simple. A thicker fog hides a lamp more than thin mist. The reason it matters is direct. When the wind grows dense, the visible surface shifts outward into the wind itself. The star's true surface can be buried. The photosphere becomes an effective layer in the outflow. This unlocks a quiet point. What looks like the star's radius may actually be a wind radius. The second concept is a stripped envelope. A stripped envelope is an outer layer removed by wind and radiation. The example stays plain. Layers are lifted away in steps. Each step exposes hotter gas beneath. The reason it matters is practical. Exposed hotter layers alter the star's spectrum and increase wind driving. This creates feedback. Hotter light pushes more strongly on ions in the wind. The wind then removes more mass. The star's identity shifts. It can move toward a hot luminous state with less hydrogen at the surface. The view drifts inward to the wind base. There the flow accelerates. It is not smooth. It breaks into clumps. Clumps form because radiative driving is unstable. Small density differences grow. Dense knots shield regions behind them. Shielded regions cool and thicken. This produces a mottled pattern in the inner wind. It resembles a slow-moving field of drifting seeds in water. The analogy remains distinct. It keeps the motion gentle. A payoff arrives in this pattern. Clumping changes how mass loss is estimated. A dense clump emits and absorbs differently than a smooth wind. Brightness in certain lines can be dominated by knots. That means apparent wind strength can be misleading if clumping is ignored. This leads into a limit of observation. The wind cannot be resolved into individual knots at most distances. Signals combine over many clumps and many paths. The same observed brightness can match a dense smooth wind or a less dense clumpy wind. Models must assume a clumping factor and geometry. Those assumptions affect inferred mass loss rates. The uncertainty is specific. It comes from limited resolution and line formation physics. The broad conclusion remains steady. Mass loss is strong and structured. The star's outer layers thin. The surface composition changes. One number anchors the timescale for major envelope removal. The transition toward a strip state can occur over about 100,000 years. That span is like a brief drift compared to the star's earlier millions. The scale shift is calm. Individual clumps change in hours to days as they form and disperse. The overall envelope changes over thousands of years. The star's evolution proceeds over tens of thousands of years. The environment records this history. The wind carries material outward and piles it into shells. Older shells move farther out and fade. Newer shells remain brighter and closer. The crescent-shaped shell expands and thins. Its curvature stays, but its edge becomes less sharp. Farther out, it merges into the larger shroud. The shroud itself interacts with the earlier bubble wall. A thin compression zone forms where the fast wind meets slower, older outflow. This zone can appear as a faint ring with an uneven brightness. The ring is not perfectly circular. It is distorted by density gradients in the surrounding medium. Another payoff arrives here. Mass loss is not only removal, it is sculpting. The star shapes its future surroundings into layered structures that later shocks will cross. The star also shapes its own future by altering how much mass remains near the core. The inner burning continues. Helium burning can proceed deeper down while hydrogen becomes scarce at the surface. The envelope becomes lighter and less able to buffer changes in the core. The star becomes more compact in some stages, yet its wind can remain dense. The effective photosphere can move inward and outward depending on wind density. Light behaves as a traveller through changing thickness. When the wind thickens, the visible layer moves outward. When the wind thins, the visible layer retreats inward. This creates slow variability without sharp flares. The wind becomes the star's visible face for long intervals. The section closes with a soft forward motion. The outer layers are now thinner and more dynamic. The core is moving toward more advanced burning. The next section follows the balance between radiation and gravity, as the wind strengthens further and as mass loss continues to set the conditions for the final fate. A massive star loses mass fastest when its own light comes close to matching its own gravity. The wind strengthens because radiation becomes efficient at lifting ions from the surface layers. At this distance, the star appears wrapped in a bright inner shroud. The shroud is not featureless. It shows a soft inner boundary where the flow begins to accelerate. It shows a mottled texture where clumps form and dissolve. The outer edge fades into a wide halo. The halo is uneven and slightly flattened. A thin, bright band sits near the equatorial plane. That band is a density enhancement in the outflow. It bends light through scattering and absorption. It also casts a broad, gentle shadow into the polar directions. The shadow is not dark like an eclipse. It is a reduction in brightness within the wind. The visual anchor settles on a spiral-like streak in the halo. The streak curves outward and slowly opens. It is made by rotation and clumping together. It resembles a ribbon of cream stirred into warm tea, yet it is gas density traced by light. This section unlocks a clear point. Mass loss can be driven by light without needing violent eruptions. The first concept is radiative driving. Radiative driving is wind acceleration by momentum carried in light. The example stays quiet. Photons are absorbed by ions. Each absorption gives a small push. Many absorptions create a steady outward acceleration. The reason it matters is direct. In very luminous stars, this push becomes strong enough to lift large amounts of gas. The second concept is an Eddington limit. An Eddington limit is when radiation pressure balances gravity. The definition stays short and stable. The example is plain. If outward push matches inward pull, gas can hover and then drift outward. The reason it matters is simple. Near this limit, small changes in opacity can change mass loss dramatically. Opacity enters as a physical lever. In hotter layers, different ions dominate. Each ion absorbs light at certain wavelengths. If absorption lines are strong, the wind feels a stronger push. If lines weaken, the push decreases. This makes wind sensitivity a central feature. A small payoff arrives here. Wind strength depends not only on brightness, it depends on which ions are present and how clumped the flow becomes. The scene moves closer to the inner shroud. There the outflow accelerates from slow to fast. The acceleration is not uniform. It happens through many small pushes. Clumps form in the wake of stronger pushes. The clumps then create shadowed regions behind them. Shadowed regions receive fewer photons. They accelerate less. They become denser. This feedback strengthens clumping. The inner shroud becomes patchwork. Bright patches mark thinner channels where light escapes. Darker patches mark thicker knots where light is absorbed and re-radiated. The edge of each knot is a gradient. Density rises smoothly toward the center of a clump. It then falls smoothly outward. Those gradients create soft boundaries rather than sharp shapes. The spiral streak in the halo becomes clearer. Rotation gently winds the pattern. The pattern is not a rigid structure. It drifts and smears, yet it persists as a curved density enhancement. A single number anchors the flow speed without harsh units. The wind can reach about 2,000 kilometers per second, like a storm front crossing a continent in minutes. The comparison is only a sense of scale. The scale shift follows. Near the surface, ions absorb photons in tiny fractions of a second. In the outer halo, the wind takes days to travel a distance comparable to the star's radius. Over years, the wind fills the bubble carved earlier. Over thousands of years, it builds shells and arcs that will remain long after the star changes. Another payoff follows from the speed. A fast wind collides with slower, older outflow. Collision creates shocks. Shocks compress gas into thin sheets. Sheets can become unstable and ripple. Ripples fold into filaments. Filaments appear as faint threads in the halo. These threads are physical traces of interaction between wind phases. The view pulls back to show the larger cavity. The cavity's wall is now more structured. It contains multiple layers. Each layer corresponds to a past wind regime. The layers are not concentric circles. They are offset and warped by density in the surrounding cloud. The star's light illuminates them unevenly. This creates bright arcs and dim lanes. Light behaves as a painter working with uneven canvas thickness. Thicker regions glow differently than thin ones. Another limit of observation appears here. The mass loss rate cannot be read directly from brightness alone. Emission depends on density squared in many processes. Clumping therefore biases the signal upward. Without resolving clumps inferred, mass loss can be too high. Also, the Eddington proximity cannot be measured directly. It must be inferred from luminosity and mass is difficult to constrain in late stages. A signal would combine uncertain distance, uncertain wind clumping, and uncertain composition. Multiple parameter sets can produce similar spectra. The uncertainty is not vague. It comes from degeneracy in models and from limited spatial resolution. Even with that limit, the key behavior remains steady. Near the Eddington limit, radiative driving becomes efficient. Opacity variations and clumping modulate the wind. Strong wind removes the envelope and shapes the surroundings. The spiral streak continues to unwind in the halo. It widens and fades as it moves outward. The inner shroud thickens briefly and then thins. This variability stays gentle. No sharp flare is needed. The star is moving toward a state where surface hydrogen can be greatly reduced. The interior continues advanced burning. The outer layers continue to be lifted and carried away. The section ends with a soft forward turn. The next step follows how the star's interior transitions into more complex burning, while the stripped outer layers expose a hotter core and set the stage for late-life structure. A massive star can look smaller and hotter after losing mass even while its interior grows more layered. The star shifts because the envelope thins, and the core begins a new fusion stage that changes the internal pressure pattern. At this distance, the bright central source appears cleaner than before. The dense wind still exists, but the effective photosphere retreats inward. The star's edge becomes more defined. A narrow gradient remains at the limb, yet the halo is less bloated. The surrounding shroud still shows clumps, but the clumps are more transparent. The spiral streak seen earlier loosens and fades outward. Closer in, a different structure appears. A thin, bright belt encircles the star. It is a wind compression zone in the equatorial plane. The belt has a sharp inner boundary. It softens outward into a fading haze. That boundary is a physical detail. It marks where density and opacity rise enough to redirect escaping light. The visual anchor settles on this belt. It resembles a thin scarf of vapor wrapped around a glowing sphere, drifting and fraying at the edges. The first concept is helium burning. Helium burning means helium nuclei fuse into heavier elements. The definition stays short. The example remains calm. A new fuel begins when the core becomes hot and dense enough. The reason it matters is direct. Helium burning changes the core's temperature and pressure profile. It also changes how quickly later stages can follow. The second concept is a convective core. A convective core is a region where hot gas rises and cool gas sinks. The definition is brief. The example is simple, like thick soup that slowly circulates when heated from below the core, overturns and mixes. The reason it matters is practical. Mixing redistributes fuel and ash. It affects how long burning lasts and how sharp layer boundaries become. A payoff arrives early. When helium ignites, the core does not merely add energy. It reorganizes the interior. The helium core that contracted earlier becomes an active engine. The hydrogen shell remains outside it. The star now contains two major power sources in different layers. The envelope responds by adjusting again. It can contract somewhat as hotter radiation escapes more easily through a thinner outer layer. This explains the surface shift without drama. The star can become hotter in appearance while still being in a late evolutionary stage. The view differs inward through imagined layers. The helium-burning core is compact. Above it sits a hydrogen-burning shell. Above that lies a wide envelope where density drops quickly with radius. The drop creates a steep gradient. That gradient sets how sound waves and convection behave. It also sets how the star vibrates. The surface can show slow variability, but the deeper work is in the core. One number anchors the time scale. Helium burning can last about 500,000 years, like a quiet interlude between longer and shorter chapters. The scale shift follows naturally. Individual convective plumes turn over on timescales of weeks to months. The overall helium fuel supply changes over hundreds of thousands of years. The outer wind structures drift outward over years and decades. These clocks overlap without conflict. The equatorial belt persists while clumps come and go. The belt's brightness varies as density variations pass through it. It casts a wide, soft shadow into the polar wind. Light behaves as filtered through a denser lane. The wind above and below looks clearer. This anisotropy matters. It changes where mass loss is strongest. It can shape the surrounding shells into a slightly pinched form. Farther out, the old bubble wall becomes dimpled. Compressed regions brighten faintly. Thin regions fade. Another payoff arrives here. Late-stage mass loss does not only remove mass, it imprints geometry that can persist into the final explosion environment. The belt is a near-star structure, but its influence reaches far. Over time, the outflow builds a circumstellar medium with layered density. Later shocks will travel through this medium. The shock's brightness and shape will depend on the density pattern. This builds the arc of consequence without introducing a cliff. A limit of observation appears softly. The star's internal burning stages cannot be directly verified from the surface alone. Surface temperature and wind lines provide clues, yet they can be influenced by clumping and composition. Helium burning affects neutrino production and core structure, but those signals are not directly accessible at these distances. A signal would be dominated by photons from the wind and surface. The deeper core remains hidden. Models infer helium burning from luminosity and spectral signatures of surface composition. Those inferences depend on uncertain mixing and mass loss history. The uncertainty is specific. It comes from degeneracy between internal mixing and external stripping. Even so, the main sequence of events remains steady. Hydrogen burning moves to a shell. Helium burning starts in the core. The envelope becomes thinner. The wind continues to remove mass and sculpt the surroundings. The visual anchor returns to the equatorial belt. Its inner edge stays sharp. Its outer edge frays into wisps. A faint ripple runs along it like a slow-travelling wave. The ripple is a density variation. It moves around the star as rotation carries it. The halo beyond remains quiet. Clumps drift outward and dissolve into the wider cavity. The overall brightness remains strong, but the environment feels cleaner and more open than in earlier phases. The section ends with a gentle turn forward. After helium burning, the core will contract again and heat further. The next section follows how the star builds more layers as burning stages multiply, and the interior clock speeds up. Deep inside, a massive star time begins to compress as new fuels ignite in rapid succession. The interior becomes layered because each fuel burns in a shell and leaves ash that sinks inward. At this distance, the star's outer appearance remains bright and hot. The wind still carries away material, yet the main action is now hidden. The surface light is steady enough to seem calm. The interior is no longer simple. A slow, imagined cutaway reveals nested layers. Each layer has a distinct temperature gradient. Boundaries between layers are not hard walls. They are transitions where composition and density shift. The visual anchor settles on an onion-like cross-section. Thin glowing bands surround a darker core. The bands are stacked with clear spacing. The spacing is not equal. Inner bands are thinner and more intense. Outer bands are broader and softer. This image unlocks the key behavior. Later, burning stages occupy less volume and less time than earlier ones. The first concept is shell burning. Shell burning means fusion in a thin layer around a core. The definition stays brief. The example is calm. Hydrogen can burn around a helium core. Later, helium can burn around a heavier core. The reason it matters is direct. Shell burning builds layers of ash that set the final collapse structure. The second concept is neutrino cooling. Neutrino cooling is energy loss by weakly interacting particles. The definition is short. The example is plain. Neutrinos pass through dense matter with little scattering. The reason it matters is essential. As the core heats, neutrinos carry away energy that photons cannot remove efficiently. This accelerates contraction and shortens late burning stages. A payoff arrives early. The star's late life is not fast because fusion becomes efficient. It is fast because the core cannot hold heat as easily. Neutrino cooling drains energy. Gravity then tightens. Temperature rises again. New fuels ignite, the cycle repeats. The view drifts inward to the helium-burning core. Helium burning produces carbon and oxygen. When helium becomes scarce, the core contracts again. Carbon can ignite if the core becomes hot enough. Carbon burning creates neon and magnesium, among other products. After carbon, neon and oxygen burning can follow. Each stage occurs deeper and in thinner regions. Each stage leaves heavier ash. The core becomes denser. The pressure becomes more dominated by the behavior of electrons and nuclei rather than by ordinary thermal motion. The onion-like layers become more distinct. A thin carbon-burning shell can sit beneath a helium shell. An oxygen-burning shell can sit beneath a carbon shell. These layers can coexist. They can also switch in strength as conditions change. The layers are not static. They pulse in power. Convection can arise in each burning shell. Convection stirs each shell's fuel and ash. It makes the shell more uniform in composition. It also creates boundaries where mixing stops. Those boundaries can be sharp in composition even if smooth in density. A micro payoff lands here. The final core is not made by one burn. It is built by many overlapping burns that each carve a layer. The number that anchors the speed up can be simple. Oxygen burning can last about 1 year, like a brief seasonal cycle compared to the earlier 100,000-year stages. The scale shift follows smoothly. At the surface, the wind structures drift outward over years and decades. Deep inside, a full burning stage can begin and end within a year. The core's state can change faster than the outer wind can reshape itself. This mismatch creates a quiet tension. The star can appear steady while its core races ahead. The onion image shifts slightly. Inner shells become thinner and more luminous. The core in the center becomes darker in the cutaway. Darkness here is not emptiness. It is a region where light is trapped and neutrinos do the carrying. Light behaves as slow diffusion. Photons scatter countless times and take a long time to escape. Neutrinos escape almost at once. This is a limit of intuition. Ordinary experience expects heat to leak outward as warmth. In the late core, heat leaks as particles that barely interact. That makes the interior difficult to imagine with everyday analogies. A limit of observation follows as well. Surface light cannot reveal the exact sequence of inner shells. Spectra show surface composition and wind properties. They do not show a direct map of the nested burning zones. A signal would be dominated by the outer layers and the wind. The core's neutrino losses are not visible in light. The thickness of each shell must be inferred from models of stellar structure. Those models depend on uncertain mixing rates and rotation. Different assumptions can produce similar surface temperatures. The uncertainty is specific. It comes from hidden interior transport and limited constraints on late-stage clumping and mass. Even with that limit, the broad picture remains reliable. Burning shifts from core to shells. Each new fuel stage is shorter. Neutrino cooling accelerates the sequence. The core becomes heavier and more compact. The outer layers continue to be stripped. Another payoff arrives as the layers build. The star's final fate depends on the mass and composition of the core at the end of this sequence. A more massive core will collapse differently than a lighter one. Envelope stripping also matters. It changes how much material falls back later. It changes what remains bound. It changes how the final explosion interacts with surrounding shells. The onion-like cross-section holds steady in the mind. Bands glow in layered order. The outermost bands feel broad and slow. The innermost bands feel thin and urgent. The view then pulls back to the star's exterior. The equatorial density belt from earlier phases can still exist. It drifts outward and fades into the cavity. New shells continue to form and expand. The environment becomes a record of repeated winds and pulses. The interior becomes a record of repeated burns. This section ends with a soft forward turn. The next section follows the approach to an endpoint. The core begins to build iron-rich ash that cannot provide further fusion support, and the star's layered structure becomes a quiet trap. The final fuel stages of a massive star end not with brightness, but with a quiet dead end in the core. The core becomes trapped because iron-rich ash cannot release energy through fusion the way lighter fuels do. At this distance, the star's exterior still shows wind structures and a clean, hot glow. The surrounding cavity still holds layered shells. Yet the interior clock has reached a narrow threshold. The onion-like layering remains. Inner shells burn briefly and then fade. Outer shells continue longer and then weaken. In the center, a new kind of core grows. It is dense and compact. The core's boundary is a steep density gradient. Inside, matter is pressed tightly. Outside, shells remain comparatively loose. The visual anchor settles on a dark central bead within the onion cross-section. Around the bead, thin, luminous rings flicker in imagined light. The rings are burning shells. The bead is the iron core. The key unlock arrives early. Iron does not support the star by burning. It supports the star only by existing as mass and pressure until it cannot. The first concept is an iron core. An iron core is a central region made mostly of iron group nuclei. The example is calm. Ash from earlier burning settles inward and accumulates. The reason it matters is direct. Iron fusion does not release energy under stellar conditions. The core can no longer gain pressure support by burning heavier fuel. The second concept is electron degeneracy pressure. Electron degeneracy pressure is resistance from packed electrons. The definition stays short. The example remains simple. Like a crowded room where movement becomes impossible, electrons resist being squeezed into the same states. The reason it matters is essential. This pressure can support the core for a time even without fusion. Yet it has limits. As the iron core grows, gravity strengthens. Temperature rises, but temperature is no longer the main support. Neutrino cooling continues to remove heat. The core contracts further. Contraction raises density. At very high density, electrons are forced into nuclei. This reduces electron pressure. The core loses its main non-thermal support. This is another small payoff. Collapse begins not because gravity suddenly changes, but because the core's internal support quietly erodes. The scene shifts from the onion cross-section to a close view of the core boundary. The boundary is not a sharp line. It is a steep gradient. Density changes rapidly over a short distance. Pressure changes with it. Above the boundary, the silicon and oxygen shells remain active for short intervals. Their energy output supports the layers above, yet their support cannot reach the center fast enough. Light behaves as slow diffusion in these deep layers. Photons scatter and take a long time to travel outward. Neutrinos escape more directly. This mismatch becomes the new driver. Energy leaves the core faster than it can be replaced by burning. The core continues to contract. One number anchors the speed of the last approach. The final silicon burning can last about 1 day, like a brief tide cycle before stillness. The scale shift is calm. A burning shell can change in hours. The wind outside changes over years. The shell layers in the circumstellar medium change over centuries. The star contains clocks that no longer align. The surface can remain steady while the core rushes. Another payoff follows from the day-long scale. The core's final decision is swift compared to the star's lifetime. The star's life has spanned millions of years. The endpoint arrives within a day of the last burning stage. The interior becomes a quiet trap. The iron core grows until it crosses a stability threshold. Gravity overwhelms electron degeneracy pressure. Collapse begins. Collapse is not a visible inward motion at the surface. It begins in the central region. The inner core falls inward. It speeds up rapidly. Outer layers follow later. The physical detail remains in gradients and boundaries. The collapsing core has an inner region that compresses nearly in step. Outside it, matter falls in supersonically. A shock forms when the inner core stiffens. The shock is a pressure wave. It starts at a boundary and moves outward. This is where intuition can slip. Everyday experience expects compression to bounce outward smoothly. In the stellar core, energy is drained by neutrinos. The shock can lose energy. It can stall. The shock's fate depends on delicate balance between pressure infall and neutrino heating. This is a limit of intuition. Small changes in core mass and structure can change whether the shock revives. A limit of observation follows as well. The core collapse and shock behavior occur behind layers that are opaque to light. Photons cannot escape from the deep interior in real time. Only neutrinos and gravitational signals would leave promptly. Those signals are hard to capture and interpret. Even if detected, they would not provide a crisp map of the internal layers. The details must be inferred from models and later debris patterns. The uncertainty is specific. It lies in the exact transport of neutrinos and the exact structure of shells at collapse. Even with that limit, the broad sequence remains steady. Iron core forms, electron support reaches its limit, collapse begins, a shock forms and struggles. The visual anchor returns to the dark central bead. The luminous rings around it narrow and then fade. The bead tightens and darkens further. The onion layers feel less like a stable structure and more like a stacked set of falling curtains. The curtains are density shells. They begin to move inward in succession. The motion is silent. It is fast in the center and slower outside. The star's wind and shells outside remain as a quiet stage. They will matter soon, but not yet. The section ends with a gentle forward turn. The next section follows the collapse and rebound, and how an outward shock can meet the surrounding layers and wind-shaped environment. The moment of core collapse begins in darkness, yet it sets an outward wave that can reshape everything around the star. The collapse triggers a shock because the inner core stiffens and rebounds, while outer layers still fall inward. At this distance, the star's surface still looks calm for an instant in imagination. The wind shells remain in place. The cavity wall remains a faint arc. Then the interior motion dominates. The iron core contracts rapidly. Density rises steeply with radius toward the center. The inner region falls almost together. The outer core falls faster and then piles up. A sharp boundary forms where infall meets resistance. That boundary is the seed of a shock. The visual anchor settles on a pressure wave front that looks like a thin ripple traveling through layered gel. The ripple is a bright ring in the onion cross-section. It moves outward across the inner bands. Each band it meets responds differently. Some compress and heat. Some begin to break into turbulence. The first concept is core bounce. Core bounce is rebound when the inner core becomes incompressible. The definition is short. The example stays plain. Like a spring that cannot shorten beyond a limit, the core resists further compression and pushes back. The reason it matters is direct. Bounce launches the initial shock that can travel outward. The second concept is shock stalling. Shock stalling is when the shock loses energy and slows. The definition is short. The example is gentle. The wave spends energy heating and breaking nuclei as it moves. The reason it matters is essential. If the shock stalls too soon, the star may not eject its outer layers efficiently. A payoff arrives early. The shock is not guaranteed to escape just because it forms. The shock must be helped. Neutrinos stream out from the newborn dense core. Some of those neutrinos deposit energy behind the shock. Heating can revive the shock. This is neutrino heating, but it can be kept as a quiet mechanism without extra terms. Energy deposition raises pressure behind the shock. Pressure pushes the shock outward again. The layered onion interior becomes a battleground of gentle forces. Infall presses inward. Heating presses outward. The shock front wavers. It is not a perfect sphere. It can bulge in some directions and lag in others. The bulges create asymmetry. Asymmetry can seed later mixing. The wave meets the silicon and oxygen layers. These layers are dense. They resist being lifted. The shock spends energy breaking heavy nuclei into lighter ones. That process takes energy rather than releasing it. This energy sink contributes to stalling. The wave also creates a hot region behind it. That region becomes turbulent. Turbulence mixes hot and cooler gas. It can keep material in the heating region longer. That increases energy gain. Another payoff follows. turbulence is not just disorder. It can provide time for neutrino heating to act. The visual anchor shifts to the shock front itself. It is a thin shell of compressed gas. Its inner side is hot and chaotic. Its outer side is colder and falling inward. The boundary between them is sharp. It is a discontinuity in density and pressure. Yet it is not a sharp, visible edge in light. It is hidden behind thick layers. The scene stays interior and slow. One number anchors the timescale of collapse. The core can collapse in about 1 second, like a single heartbeat, in a place with no hearts. The scale shift follows gently. 1 second decides the core structure. Minutes to hours decide how the shock interacts with the star's mantle. Days to months decide how the expanding debris meets the windshells outside. The outside environment still waits. It has been shaped over thousands of years. It will now be crossed in hours and days. Another payoff arrives from the 1 second scale. The outer star does not have time to respond gradually. It is forced to react to an interior decision made almost instantly. A limit of observation appears softly. The collapse and shock happen behind layers opaque to light. Photons cannot escape from the central region during the event. Only neutrinos and gravitational signals emerge promptly. Those signals carry information, but they are hard to interpret. They do not provide a simple picture of shock shape. Most knowledge comes later from the debris and light curves after breakout. Models must fill in the hidden seconds. The uncertainty is specific. It lies in neutrino transport turbulence and the exact density profile of the inner shells. Despite this, the core sequence remains steady. Collapse leads to bounce. Bounce launches a shock. The shock can stall. Neutrino heating and turbulence can revive it. The revived shock moves outward through the star. As it travels, it heats and accelerates layers. It drives expansion. It also creates mixing between shells. Mixing can dredge inner elements outward. It can smear the clean onion structure. The wave approaches the star's outer layers. Those layers may have been thinned by prior mass loss. That thinning can make escape easier. A lighter envelope offers less resistance. The shock can reach the surface sooner. When it does, a breakout occurs. Breakout is the moment the shock reaches low optical depth and light can escape. The light release is brief compared to the star's life. The physical detail anchors the approach. The outer envelope density drops steeply near the surface. The shock accelerates in this gradient. It steepens. It compresses a thin skin. The skin heats and radiates. Light then rushes into the surrounding wind. Light behaves as a flood released from a narrow gate. It scatters through the wind and circumstellar shells. The brightness and colour will depend on the wind density and composition. The earlier shells and belts now matter. They can absorb and re-radiate the breakout light. They can create a delayed glow as the shock catches them. The section ends with a soft forward motion. The next section follows the outward explosion through the layered circumstellar medium and how the star's past mass loss turns into a visible aftermath. The star's last gift to its surroundings is not the flash itself, but the way the blast meets the layers the star already built. The aftermath takes shape because expanding debris collides with windshells and turns motion into heat and light. At this distance, the scene is no longer a single bright source. It becomes a growing volume. A forward shock moves outward into the circumstellar medium. A reverse shock moves inward into the debris. Between them, gas is compressed into a thin, turbulent region. The boundary is a physical detail. It is a contact surface where dense, swept-up material piles into a rippled sheet. The sheet is not smooth. It wrinkles and folds. Fingers of denser gas push into lighter gas. Those fingers create a lace-like edge in the expanding shell. The visual anchor settles on this lace edge. It looks like a slow, blooming dandelion seed head, made of light and shadow, yet it is a shock front tracing density ripples. The early unlock arrives in this texture. The brightness is shaped by past mass loss more than by any uniform expansion. The first concept is a forward shock. A forward shock is a wave that compresses external gas. The definition stays short. The example is plane. A fast front pushes into slower material and heats it. The reason it matters is direct. This shock converts kinetic energy into radiation as it plows through the wind. The second concept is a reverse shock. A reverse shock is a shock that travels back into the ejector. The definition is brief. The example remains calm. As outer layers slow against external gas, inner layers catch up and are shocked. The reason it matters is practical. Reverse shocks heat debris and set where different elements glow later. The scene opens outward into the cavity shaped long before the collapse. The cavity wall is not a perfect sphere. It is warped. It contains arcs, belts, and old shells. The expanding blast meets these features at different times. Where density is higher, the forward shock slows and brightens. Where density is lower, it speeds and dims. This produces an uneven shell. Bright caps appear where the blast hits dense lanes. Dim corridors appear where it runs into emptier space. Light behaves as scattered through a fog whose thickness changes with direction. Another payoff lands here. The explosion can appear asymmetric, even if the central event is nearly symmetric. The environment can sculpt the visible outcome. The lace edge thickens where dense clumps are overtaken. Each clump creates a local bow shock. The bow shock wraps around it. A small bright rim forms on the upstream side. Downstream, a shadowed wake forms where material cools and thins. These wakes can align into filaments. Filaments stretch radially. They create a faint spoke pattern in the expanding shell. The spoke pattern is not rigid. It evolves as turbulence mixes material. The contact surface between shocked wind and shocked debris becomes unstable. Ripples grow, fingers form. Mixing pulls heavy elements outward and drags lighter material inward. The once clean onion layering is partially erased in the debris, yet composition gradients can remain. Certain layers stay more concentrated in certain radii. The reverse shock heats those radii later. That timing can shift the light output over weeks and months. A single number anchors the expansion scale. The main shock can move at about 10,000 kilometers per second, like a fast storm that crosses a world in a few heartbeats. The comparison is only a sense of speed. The scale shift follows softly. On the shock front, microscopic collisions heat ions in fractions of a second. Across the expanding shell, it takes days for the front to double its radius. Across the larger cavity, it can take years to reach the old bubble wall. The environment has stored a long history. The blast now reads that history quickly. Another payoff arrives when the forward shock meets the equatorial belt created earlier. That belt is denser. It slows the shock. It forces compression into a thinner sheet. The sheet brightens. The shell becomes slightly pinched. Two brighter lobes can appear above and below the belt where density is lower. This geometry emerges without any need for an uneven core. The environment alone can guide the shape. The lace edge becomes more intricate along the belt. It shows multiple nested arcs. Each arc marks a separate density enhancement laid down in earlier winds. The blast does not erase these arcs immediately. It sweeps them into stacked ridges. Those ridges can be seen as parallel brightness bands in the shell. The bands are a physical trace of layered mass loss. A limit of observation appears gently. The true three-dimensional structure is hard to reconstruct from a two-dimensional glow. Brightness depends on density, temperature, and composition. Projection can make separate structures overlap. A filament in front can appear connected to an arc behind. Without depth, information interpretation can be ambiguous. Models must assume geometry to infer mass and energy. The uncertainty is specific. It comes from line-of-sight projection and from uncertain clumping in the circumstellar medium. Even with that, some conclusions remain robust. Strong interaction implies dense surroundings. Dense surroundings imply significant mass loss before collapse. The contact surface continues to wrinkle. The forward shock continues outward. The reverse shock continues inward. The shocked region cools in places and becomes thinner. In other places, it stays hot and thick. Cooling can cause compression into a narrow, dense sheet. That sheet can fragment. Fragmentation creates knots. Knots drift with the flow. They can cast tiny shadows in scattered light. The lace edge becomes dotted. Another payoff follows from cooling. When gas cools, it radiates strongly. Radiated energy can brighten the remnant without needing new power sources. Interaction itself becomes a lantern. The scene pulls back. The expanding shell now occupies the cavity. It approaches the bubble wall. The wall is a broad arc with uneven density. When the shock reaches it, the shell will brighten again and slow. The remnant will begin a longer phase. The section ends with a soft forward turn. The next section follows the long cooling and mixing and how the remnant gradually settles into a quieter shape, while carrying heavy elements into its surroundings. After the brightest phase fades, the remnant becomes a quieter laboratory of motion, cooling, and mixing. The expanding shell does not stay hot because it radiates and spreads, and the structure slowly turns from glare into texture. At this distance, the remnant resembles a hollow sphere with a ragged skin. The skin is not uniform. It has knots, filaments, and faint arcs from older wind layers. The forward shock continues outward. Behind it, shocked gas cools. Cooling changes the thickness of the shell. Hot gas is puffed up. Cooled gas collapses into thinner sheets. The physical detail is the sheet itself. It can become so thin that it wrinkles like a drying film. Wrinkles turn into ripples. Ripples can break into clumps. Clumps become dense knots that survive longer than the surrounding gas. The visual anchor settles on a shell that looks like a cracked glaze on pottery. The cracks are dark lanes between brighter plates. The plates are regions of compressed gas. The cracks mark shear and cooling boundaries. The early unlock arrives here. A remnant is not a smooth bubble. It is a patchwork whose pattern records how it cooled and what it hit. The first concept is radiative cooling. Radiative cooling is energy lost by emitting photons. The definition stays short. The example remains plain. Hot gas glows and loses heat, so pressure drops and the gas compresses. The reason it matters is direct. Cooling can turn a thick, shocked region into a thin, dense shell that becomes unstable and clumpy. The second concept is mixing by instabilities. Instability mixing is interpenetration driven by density contrasts. The definition stays brief. The example is simple, like cream spreading into coffee when the boundary is stirred heavy and light layers interleave. The reason it matters is essential. Mixing spreads newly made elements outward and blends them with surrounding gas. The shell's patchwork thickens in some places and thins in others. Where the circumstellar medium is dense, the forward shock slows. Slower shock means more time for cooling. Cooling increases compression. Compression increases brightness in some bands. Where the medium is thin, the shock remains faster and hotter. Hotter regions stay more diffuse. This creates a remnant with bright ridges and faint cavities. Another payoff lands gently. Brightness can indicate not just energy but also density and cooling history. The cracked glaze pattern becomes more pronounced where cooling is strongest. Filaments lengthen. They stretch along flow lines. Knots trail faint wakes. The contact surface between swept-up wind and shocked debris remains unstable. It keeps feeding mixing. Heavy element-rich clumps can punch outward through lighter gas. These clumps can form bullet-like shapes without implying any intention. Each clump has a leading edge. That edge is a bow-shaped shock. Behind it, a tapered tail forms where material is stripped. The boundary between clump and ambient gas is sharp. It is a gradient in density and composition. Light behaves as scattered off dust and gas in different ways. Some wavelengths pass, some are absorbed and re-emitted. Dust can form in cool, dense regions. Dust formation does not require a calm environment. It requires temperature and density conditions that allow grains to grow. When dust forms, it can create self-shadowing. Bright regions behind dust lanes dim. This adds to the cracked glaze appearance. One number anchors the longer timescale. The remnant can remain hot and expanding for about 10,000 years, like a long season compared with the brief day of the final burn. The scale shift is gentle. A grain can grow over months in a dense knot. A filament can evolve over decades. The whole remnant can expand and cool over thousands of years. Beyond that, the surrounding interstellar medium responds on even longer times. Another payoff follows from the long span. The remnant has time to mix elements far beyond the original star's radius. It becomes a conveyor of composition. The shock front sweeps up ambient gas. Swept-up mass grows with time. Eventually, swept-up mass can exceed the original ejector mass. When that happens, the remnant's behavior changes. It transitions from ejector-driven expansion to a more Sedov-like phase. The term can be avoided. The idea remains. The remnant becomes governed by the energy of the blast and the density of the surroundings, rather than by the original debris alone. The shell thickens again in some regions as it becomes more uniform, yet the patchwork does not vanish quickly. Fossil structures persist. Old wind shells remain as arcs. They can be re-brightened when struck. The cavity wall can create a secondary bright ring. When the forward shock reaches the wall, it slows abruptly. Compression increases. A new set of ripples forms. The cracked glaze pattern gains a second boundary. This can create nested rings. Nested rings are a physical signature of layered surroundings. A limit of observation appears softly. Even when rings and filaments are seen, their ages and origins can be confused. Different processes produce similar arcs. Projection can turn a sheet into a ring. Cooling can mimic a density enhancement. Without full velocity, information interpretation remains uncertain. Models must guess the three-dimensional distribution and clumping. The uncertainty is specific. It lies in unknown distances along the line of sight and in unknown small-scale density contrast. Even with that limit, the slow trend is clear. Expansion decelerates, cooling increases, mixing spreads elements. The remnant gradually merges with the ambient medium. The shell becomes less distinct. Pressure equalizes. Turbulence fades. The heavy element-enriched gas becomes part of a larger reservoir. The cracked glaze pattern softens into faint mottling. The section ends with a gentle forward turn. The next section follows the final settled outcomes and how the star's life cycle closes into a calm perspective of matter and time. When the last fast motions fade into quieter drift, the life cycle of a massive star becomes visible as a change in texture, not a single event. The end state is a remnant that disperses energy and elements into its surroundings, while a compact core remains as a dense boundary. At this distance, the scene holds two parts. One part is the expanding remnant shell. The other part is the compact object at the center. The shell grows wider and thinner. The compact object stays small and intense. The physical detail is the gradient between them. Density drops steeply from the central region into a low-density cavity. Across that gradient, pressure slowly equalizes. The shell's outer edge is still marked by a shock. That shock weakens with time. It becomes less sharp. It turns from a violent discontinuity into a broad compression. The visual anchor settles on a pale bubble in a dark field. The bubble's rim is faint. Inside, filamentary haze drifts like smoke in still air. The smoke is not calm, but it moves slowly on the scale of years. The early unlock arrives in the dual structure. The final fate is not only collapse or explosion, it is also redistribution. The first concept is the compact remnant. A compact remnant is a collapsed core left after a massive star dies. The definition stays short. The example remains plain. It can be a neutron star or a black hole depending on mass and fallback. The reason it matters is direct. The core stores much of the star's original gravity in a small volume. The second concept is enrichment. Enrichment is the spreading of heavy elements into surrounding gas. The definition is brief. The example is gentle. Like pigment diffusing through clear water, heavy atoms from the interior mix outward over time. The reason it matters is simple. The surrounding medium changes composition and cooling behavior after mixing. The shell continues to sweep up ambient gas. As swept-up mass grows, the remnant's expansion slows. Pressure differences diminish. The interior becomes less overpressured. Filaments thin and break. Knots dissolve. The cracked patterns from earlier sections soften into faint mottling. Yet boundaries remain. A faint rim outlines the shock. Inner arcs trace older shells. Each arc is a memory of mass loss. The remnant has a layered past recorded in curved lines. Another payoff arrives in that geometry. The environment and the star co-author the final shape. The star builds shells. The explosion lights them. The remnant carries them outward. Light behaves as a quiet messenger here. It can only reveal where gas is hot, dense, or dusty enough to radiate. Much of the mass can be cold and nearly invisible. The compact remnant at the center can also be quiet. If it is a neutron star, its early heat fades with time. If it is a black hole, it can remain dark unless surrounded by dense fallback or ambient gas. The final fate, therefore, cannot be read from brightness alone. A limit of observation appears softly. The compact object is tiny compared to the remnant. Its radius is far below direct imaging at large distances. The interior of the remnant is also a three-dimensional structure seen in projection. Filaments can overlap. Voids can hide mass. Estimates depend on models of temperature ionization and clumping. The uncertainty is specific. It lies in unseen cold material and in unknown filling factors of dense knots. Even with that limit, the broad arc remains clear. Massive stars turn hydrogen into heavier elements in nested shells. They lose mass and carve bubbles. They collapse and launch shocks. The shocks mix and spread material. Over thousands of years, the remnant merges with the interstellar medium. One number anchors the calm, long view. The full remnant phase can last about 100,000 years, like a slow tide compared with the short flash of breakout. The scale shift follows gently. Nuclear burning takes millions of years. Collapse takes seconds. Shock breakout takes minutes to hours. Remnant mixing takes tens of thousands of years. The same object spans extremes of time. Another payoff arrives from that span. The explosive end is only a brief hinge in a much longer process of transformation. The remnant's energy becomes heat in surrounding gas. That heat drives sound waves and turbulence. Turbulence slowly decays. As it decays, gas can cool and compress in places. Compression can form denser patches. Those patches can later become new clouds. The remnant does not force a direct outcome. It changes probabilities. It changes cooling rates by adding heavy elements. It changes density by sweeping up and compressing. The compact remnant remains as a gravitational point in the center of an emptied cavity. The cavity itself can eventually refill as ambient gas drifts in. Dust can settle, magnetic fields can be bent and tangled. Yet time smooths most edges. The faint rim becomes harder to distinguish. The last visible arcs fade. The bubble becomes indistinguishable from the larger medium. The enriched material remains. It disperses beyond the original bubble. It becomes part of a broader chemical landscape. The section closes with a soft stabilization. The life cycle completes without a sharp ending. Motion becomes drift. Heat becomes warmth in dilute gas. Structure becomes a gentle gradient that blends into the dark.